It feels steady, linear, predictable. 1 second always follows another. But in the vast and warped landscape of the cosmos, time behaves very differently. Welcome to the strange world of time dilation, a phenomenon where time doesn't tick at the same rate for everyone. It stretches, bends, and even slows down, depending on how fast you're moving or how close you are to gravity. Time dilation isn't just science fiction. It's real physics. It's been measured, observed, and confirmed. And if you want to understand black holes, space travel, or even your GPS, you need to understand how time bends. Time isn't absolute. In the early 20th century, our understanding of time underwent a revolution. Albert Einstein's theory of special relativity introduced a stunning idea. Time is relative. According to Einstein, the faster you move through space, the slower you move through time, from the perspective of a stationary observer. In other words, if you're traveling at near the speed of light, your time slows down compared to someone who's standing still. This isn't a metaphor, it's measurable. This effect is known as kinematic time dilation, and it's been proven by countless experiments. The twin paradox. One of the most famous examples of time dilation is the twin paradox. Imagine two identical twins. One stays on Earth. The other boards a spaceship and travels near the speed of light for a few years, then returns. Due to time dilation, the spacefaring twin would have aged less than the one who stayed behind. Maybe by just a few months, or maybe by decades, depending on the speed. This isn't just theoretical. In fact, we've measured time dilation using high-speed jets and incredibly accurate atomic clocks. Astronauts aboard the International Space Station actually age slightly slower than people on Earth, though by fractions of a second. Gravity slows time. Einstein didn't stop at special relativity. He went further, developing general relativity, which describes how gravity warps time. According to this theory, the stronger the gravitational field, the slower time passes. This is called gravitational time dilation. Near a massive object, like a black hole, time ticks more slowly compared to areas with weaker gravity. If you stood on the edge of a black hole just outside the event horizon, an hour might pass for you, while years pass for someone far away. This isn't science fiction. It's the very idea behind Interstellar, and it's backed by solid physics. Real-life time dilation. You may not feel it, but time dilation affects your daily life. Your smartphone's GPS uses satellites orbiting Earth. Those satellites experience both types of time dilation. They move faster than we do, which makes their clocks tick slower. But they're further from Earth's gravity, which makes their clocks tick faster. To work properly, the system has to correct for both effects. If not, your GPS could be off by kilometers every day. So every time you get directions, you're using Einstein's theories. Time dilation, near a black hole. Let's revisit black holes, the ultimate playground of warped time. The gravitational pull of a black hole is so strong that time near its edge practically stops from the viewpoint of a distant observer. This means that theoretically, you could use a black hole to time travel into the future. Spend a few minutes near its event horizon, and decades might pass in the universe outside. This is one of the most extreme examples of gravitational time dilation. And it's why black holes are such powerful thought experiments in relativity. Fast forwarding to the future. Here's something fascinating. Time dilation is one-way time travel. You can't go back, but you can jump forward by slowing your own clock. If a spacecraft could approach 99.99 the speed of light, astronauts aboard could experience weeks, while years pass on Earth. This idea is central to many sci-fi concepts, like the time traveler who returns home to find centuries have passed. While we can't yet reach such speeds, time dilation tells us The future is accessible if we can move fast enough or harness powerful gravity. Implications for interstellar travel. Why does this matter? Because time dilation could be a tool for space exploration. If future humans travel on relativistic starships, they could reach nearby stars in a single lifetime, from their perspective. Meanwhile, Earth would age much faster. A journey to Proxima Centauri might take 4 years from our viewpoint, but mere months on board a high-speed vessel. The cost, of course, is the loss of synchrony. You'd return to find your homeworld much older, or unrecognizable. Still, it opens up the possibility of practical interstellar missions. Philosophical perspective. Time dilation forces us to rethink the nature of time itself. It isn't a universal clock ticking in the background. Time is local, flexible, and shaped by motion and gravity. In the grand cosmic dance, every object experiences time in its own unique way, creating a tapestry of personal timelines across the universe. The passage of time, it turns out, is one of the most personal experiences in physics. And in a strange, poetic way, relativity reminds us. We all live in different moments. Final thought. Time dilation isn't just a curiosity. It's a profound reality woven into the structure of the universe. It bends our understanding of motion, gravity, and experience itself. It's the reason black holes freeze time, the reason GPS works, the reason time travelers may someday leap forward. And it's a reminder that time, like space, is not fixed, but a dimension we're only beginning to explore. Here on Infinity Beyond, we're not just watching the clock. We're watching how the clock changes. Because in a universe where time bends, the future belongs to those bold enough to chase it.